the total volume of these capillaries, if it is more, then it will lead to lower strength. So we are designing a concrete and we want the heterogeneous materials, different materials, cement, water, 20 mm, 12 mm, etc. to be together. But we are incorporating, or we are making inside porous nature of concrete by putting more and more water. More the water, we are giving a chance for more evaporation, and hence more capillaries will be formed. Once the capillaries are formed, the space that should have been occupied by materials of concrete, ingredients of concrete, is occupied now today by some space, some void. Madam, change when I tell you, madam. Madam, change only when I tell you. So more the space occupied by these voids, actually, instead of the concreting materials itself, the concrete becomes porous, and then it will lead to lesser strength. That is why long back the concrete has been that is long back the concrete. There are two equations which have been made. That is, the strength of concrete is inversely proportional to water cement ratio, and then the other factor, this permeability, is directly proportional to water cement ratio. These two have come into picture because of this nature of these capillaries and the formation of capillaries and how much the space the capillaries occupy actually. Okay, so we have come to know the strength of concrete is inversely proportional to water cement ratio, and permeability is directly proportional to water cement ratio. Next slide, please. So a concrete designer, somebody who is making concrete, if we want to have a durable concrete, we need to keep the water cement ratio as low as possible, because lower the water cement ratio, higher the strength and also higher the durability. Higher the durability comes into picture because once the water cement ratio is reduced, permeability is reduced or impermeability is increased, and hence materials cannot get in and get out easily, and hence the concrete becomes naturally durable. And next, most importantly, in the initial stages of concrete setting and curing, quick evaporation of water will take place. Evaporation rates more than 1 kg per meter square per hour is not recommended. That means in situations where the evaporation is more than 1 kg per meter square per hour, you are recommended not to place the concrete, Okay, so because in those areas, in those situations, the evaporation is so high, concrete may lead to get more cracks. Also, the evaporation rates will be so high that the capillary formation, which would have or should have formed later, will form in the initial stage itself, leading to cracks and then strength loss. So how to prevent the evaporation losses? That is where the curing comes into picture. So curing is a method of keeping sufficient water inside the body of concrete, not externally filling it, but whatever water has been already added during the design of concrete, during the making of concrete, that amount of water should be inside the body of concrete. That is the meaning of curing actually. So curing has to be done as long as possible to keep the capillaries formation under control, especially in the initial stages. And you cannot just like that reduce the water cement ratio. You have to use chemical admixtures, and by using all these methods, you keep a control on the capillaries formation and total amount of capillaries. So this is how a more capillary structure or concrete with more capillaries will become weaker, and hence this equation has come into existence, which everybody knows. Next one. Next. In concrete, there are different kinds of pores, which again gives substantiation to the law of water cement ratio. One is capillary pores, which are formed due to physical evaporation of water, and then there are gel pores, which are there within the calcium silicate hydrate gel itself, which is a byproduct of cement water hydration. And there are next set of pores which are formed due to evaporation of water in between the cement paste and aggregate. So there are micropores, there are sedimentary pores. What are sedimentary pores? Once the aggregate and cement uh, everything hardens, actually concrete hardens actually, once this transition zone, the interface between cement paste and the aggregate becomes weak due to evaporation of water or due to formation of some pores in the transition zone, it will attract more and more water to evaporate through this, and the tunnel or the channel becomes bigger and bigger. These are also called as sedimentation pores or sedimentary pores. So there are several kinds of pores. The main important things are capillary pores and gel pores. Gel pores are formed between the cement paste itself, that is CS gel itself. Now it is said that the gel pores are about one third, about 30 to 35% of the total amount of pores formed in the body of concrete. All this all this put together form the space of the network of pores actually. Next one. Next one. So to make everybody clear about the water cement ratio law, okay, there are two curves actually. Two curves. On the left hand side, we have water cement ratio versus strength actually. On the right hand side, we have water cement ratio versus permeability. Okay. So the left hand side curve, everybody knows this, but just I want to tell some 2 points or few points actually about how this affects the durability and strength actually. So once the water cement ratio goes on to the right hand side, the strength comes down. So this curve shows to us, suppose we are making a good concrete. Let us say concrete has been produced in the batching plant at M40, okay, with a water cement ratio of say 0.4 or 0.38. If it comes to the site, actually, if it comes to the site, somebody can go on adding water and push the water cement ratio towards the right hand side and bring down the strength to maybe 15, 20, or 25, or whatever it is, depending upon the amount of water that is added. So a concrete which is already produced, sent to the site with a good controlled water cement ratio can be spoiled and can be degraded to lower strength by just go on adding. This is the left hand curve talks about that one. The right hand curve is a mirror reflection of the left hand curve actually, which says that as the water cement ratio goes up, the permeability also goes up. In other words, impermeability is also inversely proportional to water cement ratio. If the impermeability you want more, keep the water cement ratio down. That is why at 0.4 and below, where the impermeability becomes zero or lesser, closer to zero, we say that marine structures and structures, especially water tanks and all, where you need a high degree of water tightness and high degree of durability, you need to keep the water cement ratio 0.4 and below. So if you want to push the concrete towards durability, the first and the most important step is to keep the water cement ratio as low as possible. to push up the strength and durability. Next slide. Next slide. So we are again talking about capillary pores. As far as the permeability is concerned, the network of pores, their overall concentration, total volume, interconnectedness, diameters of pores. When we talk about the diameters, the capillary pores are larger in diameters, okay, maybe in microns. The gel pores are in nanometers. In nanometers, very small pores, okay, which can be looked in by microscope. Continuity in network of pores determine permeability. So how network is, one is concentration of network, and whether the network is connected also, in how they are connected, how the interconnectivity is there, that all depend, determine the permeability of concrete actually, which is very important. Okay, see, more the permeability, lesser the durability. So that is why this factor is important. Next one. So in short, it is completely essential to keep the water cementation down to as lower level as possible to push the concrete to higher durability. Next. Next. OPC is the largest binder material used in the concrete worldwide actually. So since its invention in 1824 by Joseph Asphalin, okay, there are not much structural changes. I mean to say, there is not huge changes that have taken place in the reactions or the chemical compositions that cement is intended to do it. There is not much changes have been built in. We agree processes have been changed. The process of manufacture has been changed, evolved for a period of time, but OPC remains as OPC for quite a long time now. Okay, and OPC has its own inherent problems. OPC has its own problems. What are the problems with OPC? These problems, the problems with OPC, which we are going to talk about, are, you can say, villainous, or like villains to the concrete actually. It undermines that OPC should not be used more, and it also says to us that there's no point in using more and more OPC. So we'll check about those parameters which are harmful to concrete in terms of durability. So first point is OPC, higher the heat, higher the OPC, higher the hydration. Okay. Okay. Now it is estimated that, let us say, a concrete is having about 350 kg per cubic meter of cement is having about, cement content is about 350 kg per cubic meter. Now let us say another mix design is done at 450 kg per cubic meter. Every 100 kg of OPC content increase will set to be increasing the heat of hydration between 13 to 14 degrees. So as the cement content goes up, the heat buildup in the body of concrete increases. This is a very big concern in moss foundations, huge structures, thicker structures, raft foundations, bigger beams, bigger columns, high grade concretes, things like that, where the cement contents are more. Okay, why it is a problem in these situations is that in these cases, the heat buildup will be so much at the center, and heat will be lesser near the surface of the concrete, because the surface will be closer to the atmosphere. It will be influenced by the atmosphere, and it will be in a lesser temperature. So if the difference in temperature between the core temperature and the surface temperature goes beyond 13 to 15 degrees, then thermal cracks will develop in the body of concrete, leading to destruction of the structure, leading to deterioration of the structure. So heat buildup in OPC mixes is a problem. So we need to be very careful about this, especially if the structures are, if the concrete is used, if such cements are used in moss foundations, raft foundations, things like that. No point in using more OPC, as we are aware the fact that water cement ratio is the one which owns both strength and durability. So there is no point. For example, earlier in older specifications, 1.5:3 mix was specified for M25 concrete. It used to be called as 8-bag mix. So 400 kg was specified earlier in many government specifications, and even 30 years back, this was a nominal mix actually, or a kind of a prescriptive mix or a prescribed mix to many. Okay, so if somebody wants M25, just use 1.5:3 like that. The situation was. Now the same 400 or 410 kgs, 420 kgs mix cements will give a strength of about M40 or M45. So from M25, same cement content will give M40 or M45 thanks to usage of enhanced or high performance admixtures. On the other hand, same M25 can be done by 300 or 320 kg mixes. So this is the current situation where, due to availability of high performance admixtures and all, the cement contents can be easily reduced, and there is no point in using high amount of OPC. When we have very clearly, you have a lot of data where with a lower OPC and lower water cement ratio, you can get higher strength. No point in using higher OPC. Most important point is, for example, if you take the concrete mix, the only synthetic product in this is cement, aggregates, and water or natural materials. But it is said that all the materials, man-made materials, all man-made materials, manufactured materials, have a tendency to go back to its natural state. So cement is the one which is in the unnatural or man-made material, which is not in its natural state, has a tendency to go back to its natural state. Okay, what is the natural state of OPC? It is limestone. Okay, so it wants to go back to its natural state, and it is waiting for an opportunity to be attacked actually, or to be assisted to go back to its natural state. Okay, so external agencies like chloride, sulfates, water, oxygen, carbon dioxide, all these agencies will help the cement or the hydrated cement to go back to its natural stage, which is limestone. So when you have more and more OPC in a mix, that means you have created a product with a unstable ingredient, unstable product which wants to go back to its natural state, which is limestone. Several other metals are there like PVC and all. It will take longer time to go back to its natural state. Next. OPC production is accompanied by a huge amount of production of carbon dioxide, which is a greenhouse gas, and it is said to be one of the major factors responsible for global warming. We all know that more the carbon dioxide and other gases produced by human activities, different activities, automobile industry, burning of fuels for various purposes, and then cement production, all these things put together are, you can say, spitting carbon dioxide like venom into the atmosphere, disturbing the carbon dioxide levels and other levels in the atmosphere, and being responsible for heat buildup in the planet Earth, on the planet Earth. And it is said that if the same things continue for longer times without any change by cement producers and other manufacturers manufacturing in such a way that they are all responsible for production of more carbon dioxide. it may lead to higher buildup of heat, which will eventually cause huge amounts of ice to melt in places like Antarctica, wherever the ice is there, and the sea levels are set to go higher, and then coastal places, coastal areas will be almost submerged, and there will be havoc or destruction, mass destruction will happen actually. So, as civil engineers, we should move away from this kind of production of OPC as much as possible, contain the production of OPC, encourage the production of blended cements or blended concretes actually, so that we are not only making a good concrete, durable concrete, also we are demonstrating to people of the planet that we are responsible. So this is a important point other than durability, but which has a significant impact on the temperature buildup of the earth. Optimized cement content mixes will have positive effect on durability and also makes concrete greener. Also, another point is there that when you have a good aggregate to cement ratio, not only water cement ratio, there is another contributor for durability, aggregate cement ratio. If the aggregate cement ratios are better, optimized, controlled, that also will increase the durability. So a concrete mix, a cement mix, which is having more aggregates, okay, with a same water cement ratio, and compared to a cement content mix or a concrete mix which is having a higher cement content, same water cement ratio, there is every chance that the aggregate cement ratio of the low cement content mix is at a higher level, and hence it has a better durability, chance of better durability. Of course, when we are talking about optimization of cement content and all, we need to be aware of the codes actually, codal practices of the relevant codal practices like 456 and things like that, where the cement contents or minimum cement contents are specified. You cannot go down the specified cement contents by the uh, national codes. Yeah, next. So I am always fascinated about these structures. 5,000 years back, when the people have built these pyramids, actually, they have built by limestone. Okay, the relevance of the pyramids to today's topic is that at that time, 5,000 years back, there was no OPC, there was no steel, but they were able to build such massive structures. One of the structure, which is King Khufu's pyramid near Cairo, which is about 458 feet, and is said to have been made with about 3 million blocks of stone. 3 million blocks of stone. They have not used steel. So OPC and steel, all the villains, or you can say they are on one side. They have aided taller constructions, bigger constructions. On the other hand, the durability is a question mark as far as these materials are concerned. When you have OPC concrete with embedded metal, that is the problem. That is where the corrosion starts, and that is where the problem starts. So, next one. Next one. So, probably the builders of these pyramids were knowing that they should not use such materials, especially with embedded metals. And that is how they have won a race against time. 5,000 years is not a small time, actually. 5,000 years is a huge time. These structures have passed their life, actually. Means against rain, shine, whatever it is. Okay. Now, another interesting point with respect to pyramids is Professor David Ovitz in 1980s. Professor David Ovitz, the French scientist who talks about, who is regarded throughout the world as father of geopolymer concrete, makes a theory that some of the stones, at least, have been made with geopolymer concrete. Geopolymer concrete, at that time, there was what you can call as volcanic ashes, things like that, and some activators they used, and using that one, they have passed these stones in situ. Why? Because very close to that place there are no big stone quarries, and all the stones have to be uh, transported through River Nile, and that is not a, it is a humongous task actually. It is not a easy task actually. So this man proposes theory of geopolymer concrete, and so of course whether people agree or not, some scientists have a different theory. All these things are there, but the point what I want to draw your attention is OPC was never considered as a very durable metal, and 5000 years back that kind of metal was not there and was not used, or probably they were knowing that such metals should not be used if they want to build in their system durability. Next one. Next one. Yeah. So we cannot just like that reduce the OPC content to make a durable concrete. Okay, we need the help of chemical admixtures. Okay, we need to use certain dosage of chemical admixtures, HRWRA. Okay, whether it is SNF based or PC based or whatever it is. Okay, and bring down the water cement ratio. And bringing down the water cement ratio is dependent on the water reducing capability of these admixtures. PC admixtures, the modern day, the latest generation of admixtures gives a water reduction of about 30 to 40%. So now it is easy to produce 0.25 with water cement ratio of 0.25, pumpable concrete, easily placeable flowing concrete, things like that, which was never possible earlier. So if you want to push the concrete to higher levels of durability, you need to have low water cement ratio. That can be achieved by using high performance, high range water reducing admixtures. Next, next. Aishwarya, can you change slide? Next slide. Next slide. So the next set of materials which are used to push the concrete to higher level of durability are mineral admixtures. As everybody knows, pozzolanic materials, it is not a new material or something like that. Okay. Uh, Pozzolanic materials were first found in a village called Pozzoli in Italy 2000 years back. Romans used this in a very big way. You have many structures like Roman Colosseum and many structures, including some structures, non-Roman structures, 300 BC and things like that, where it is said that they have used some form of volcanic ash, and it is also said they mixed with lime and animal blood or many other materials, hair of horse, things like that, to make durable plasters and concrete-like thing, actually, concrete-like material. Actually. So mineral admixtures or pozzolanic metals are not a new phenomenon, actually, but it is existing for quite some time now. And these are really materials which have made a significant impact on the development of durable concrete. The first contribution comes from chemical admixtures, and the second contribution comes for durability, higher durability, when the chemical admixtures are used in conjunction with mineral admixtures. Next, next. So by using SCMs, what are the benefits that you get to make it overall durable? Permeability, resistance to chlorides, resistance to sulfates, carbonation, um, alkali silica reactivity, drain shrinkage, creep. All the above properties are improved significantly or kept at same levels by using SCMs. Some of the parameters of durability are either at same level, whereas many of the important properties are enhanced significantly, especially some of them are permeability, which are significantly enhanced, resistance to chloride, sulfates. All these are enhanced significantly when we are using SCMs, by which the SCMs push the concrete to higher degree of durability. Next. Next. So reduced permeability. When the pozzolanic materials react with the products of hydration of cement, which is frame lime or other things, then in the capillaries form, the further calcium silicate headed gel goes on developing, goes on depositing itself, making the concrete more denser and denser as the time changes, as the time elapses actually. Okay, so that means the concrete with SCM, with any SCM, whether it is fly ash or GGBS or microsilic or metakaolin or isoskash, the phenomenon is almost similar. Okay, small changes will take place, but it is not significant. So whether you are using any of these materials, whenever you are using all these materials, there will be secondary hydration going on. Because of the secondary hydration, this calcium silicate gel production will be continuous as long as the moisture is there inside the body of concrete, as long as the presence of calcium hydroxide is there inside the body of concrete. The reaction will be continuous, and the development of CSH gels will be a continuous ongoing process, or you can say a work in progress. Okay. And these CSH gels will go on filling up the capillary pores. We already talked about the capillary pores, different types of pores and all. So it will go on filling up these things, and as the concrete ages, the pore volume decreases. Professor Arun Swami has talked about this one. The pore volume is decreased by about 60% in 90 days, and the coefficient of permeability is reduced about 56% by addition of 50% GGBS. Okay. As I said, the concrete is made denser as the capillary pores goes on getting filled up by the usage of SCM. When the SCMs go on reacting with the calcium hydroxide and causing more and more calcium silicate hydrate gel formation. Next slide. Most significant effect of SCMs or pozzolanic materials is in reduction of ingress of chlorides, or I mean to say, in other words, resistance to chlorides is significantly enhanced actually when we are using SCMs. There is no way OPC can compete in this section actually. We need to remember, if you want to make simply a durable concrete, forget about OPC, because we cannot have with pure OPC very low levels of chloride and resistance. Okay, you need to do a lot of circuits. We need to do a lot of mixed designs to achieve a very low resistance to chlorides. Resistance to chlorides is also measured by ASTM 1202, which is a test for resistance to chlorides, which is measured in coulombs actually. So when we do this test, 2000, a value of 2000 coulombs is said to be moderate, and then 1000 coulombs if we get in such a concrete, it is said to be good. 500 if we get such a concrete is said to be very good, and below 500 it is said to be an excellent concrete actually. Excellent concrete, and it will push this particular factor alone can say that the concrete is going to last for a very long time. So in marine structures, wherever the chlorides are there, chlorides cause what is called as pitting corrosion, and it is a very big trigger in terms of accelerating the corrosion in the body of RCC structures. So if you want to contain the progress of corrosion, if you want to push the concrete to next level of durability, you have to control the ingress of chlorides. Okay, So the only way, or you can say the best way of doing it is using SCMs, either GGBS or fly ash, or any of the other metals like microsilica or metakaolin or things like that. Actually. Next one. Next. So this is another slide actually, which shows that at a depth of, say, for example, 25 mm, when you go to a depth of 25 mm, okay, the chlorides is at about 1.75% when you are using no GGBS or fly ash. But when we use about 60% of GGBS, okay, the chlorides are almost nil at about 25 mm. When the depth touches 25 mm, there is no availability of chlorides actually. So you can see from this graph the resistance to chlorides is significant, and this is one of the best ways of making the concrete durable in an environment where there are more chlorides available. Next. So as I said, it is not necessary that we have to stick to only OPC or fly ash or something like that. Depending upon what strength you want, what performance you want, you can change the SCMs. Okay, by using microsilicon metakaolin, we have reached RCPT values below 500. Okay, permeability as measured by DIN 1048, lesser than 20 mm, something like 14 mm, 60 mm and all, which indicates the concrete is pushed to a very high level of durability. So RCPT values, such RCPT's values as depicted here, below 500, can be easily achieved by using SCMs, and it is very difficult. I'm not telling it is impossible. It is very difficult to achieve with only OPC. Next one. So sulfate resistance is another activity that goes on when the calcium hydroxide uh, and also available products like monosulfides are attacked by external agencies like sulfates. Okay, so there are several forms of sulfate attack, and in this situation where there is a lot of sulfates in soil and water, you want to protect the concrete. The best way is to go for SCMs, and where you can make the concrete more durable. Either use fly ash or GGPS. Here, the example is given is from fly ash actually. GP represents general purpose cement, that is ordinary Portland cement. And when we are using 20% or 40% fly ash, okay, in India, the Indian codes allow up to 35%. But the example, these trials have been done somewhere else, where you can see the fly ash up to 20% or 40% has significantly changed the resistance to sulfates. So you want to make the concrete more durable. This is one of the points that you need to remember. Use SCM, either GGBS or fly ash, whatever. Next. We already had touched on this one, that about the heat buildup actually. SCMs react more slowly. Why SCMs react more slowly? SCMs will wait for calcium hydroxide to form, and the SiO2 of SCMs or the pozzolanic materials will go and meet calcium hydroxide and start consuming calcium hydroxide for forming further calcium silicate hydrate gel. So there is a delay in the progress of heat buildup. There is a delay in heat buildup actually, and for all mass concretes, mass foundations, okay, the preferred material is either you can use 70% GGBS plus 30% OPC, or a minimum of 35 to 40% of fly ash. Um, so all these higher replacements have been found to significantly contain the heat buildup actually. Okay, next one. Next one. When we are pushing the concrete to durability by using reduction in water cement ratio, by using chemical admixture, and by using SCMs, one of the other side effect that you get is long-term strength. Actually. The long-term strength after 28 days is significantly improved when we are using SCMs actually. SCMs. So for a person, for a customer who is purchasing the concrete with OPC GGBS or OPC fly ash, he need to be aware that he is getting a higher strength actually, material with higher strength. Okay, material with higher strength is getting actually at the end of say 90 days or something like that. So this is another benefit of using SCMs, and you can say it is a side effect of using SCMs, where durability, we are trying to make the concrete durable, and when you are making the concrete durable using SCMs, you are getting another, you can say, a gift or something like that from these materials, which is a unexpected or very high degree of higher strength as the concrete ages actually. Next. So a customer purchases a concrete 240 100 240 OPC 100 fly ash. This fly ash was from thermal power plant Ennur thermal power plant near Chennai. So when we use this 240 plus 100, okay, the water cement ratio around 0.49, then the 28-day strength is about 37 or 38, and there is a rise of the strength to about 55 newtons in 365 days. So you can always expect about 12 MPa or 15 MPa between 28 days to uh, 90 days. And then again, there is a improvement where it will say that you can get as good as about 12 to 18 MPa in 20 in 365 days. Okay. The long-term strengths depend upon fineness of fly ash, fineness of GGBS, how they are reacting with the particular brand of OPC, fineness of OPC, and things like that. Okay. If the fineness of all these metals are very high, most of the strengths are achieved quickly, and the long term may be stunted. Okay. So what we are talking about, if the fineness is controlled and not too high, the long term strengths are better actually, because the reactions, pathogenic reactions go on slowly. And it is said that the reactions will continue for several years as long as the availability of free lime is there in the body of concrete. And some researchers have told the reactions can continue for 30 years, 40 years actually. Okay, next. So the curve, the particular curve is shows very clearly the strength at 100%, strength at 28 days is about, if you take as a 100%, strength in 90 days was found in Coimbatore with Tuticorin. I'm talking about the average of these results from Tuticorin plant and Mettur plant. Fly ash was taken from these plants actually, and not a particular brand of OPC. Many OPC brands were used, and this curve is made after more than about 500 or 600 results. Each result is equal to average of 3 cubes. So here it shows that about jump of between 28 days to 90 days, the jump is about 40%. We have found this jump around 20% in some places, 23% to 30% in Bangalore, and in other places as good as more than 35%. For example, here in Coimbatore, when we used Tuticorin and Tour fly ash, it has gone up to 40%. So, in short, what I want to tell you is that there is a significant growth of strength beyond 28 days when we are using supplementary cementitious material, which is an offshoot of our quest for durability. Next one. Next one. So, if you want to do more durable concrete, if you want to build in another dimension, to durable concrete or durability of concrete, you can also use corrosion inhibitors. Calcium nitrate based corrosion inhibitors significantly enhance the corrosion, and they are part of uh, concretes in many places. Many places, especially in Gulf countries, where a lot of pile foundations are done, where there is a lot of sulfates and chlorides. These corrosion inhibitors are used in big quantities. For example, the calcium nitrate based corrosion inhibitor is used at a dosage of about 10 liters to 15 liters per cubic meter. Okay. Okay. So there is a lot of history actually. So apart from the added durability given by SCMs and lower water cement ratio achieved by using chemical admixtures, you can also add corrosion inhibitors to make the concrete more durable. You have other kind of corrosion inhibitors or migrating corrosion inhibitors. You have shrinkage reducing admixtures. Shrinkage is always a problem, especially the drying shrinkage. You have drying shrinkage admixtures. You have hydrophobic admixtures which coat the capillary pores and will not allow the water or other materials to get in actually, and hence making the concrete more impermeable and hence more durable. So you have many different varieties of hydrophobic admixtures, okay, which can make the concrete more and more durable. You have what is called a super hydrophobic concrete surface, okay, also, which can be achieved by using more and more this kind of additives. Next. So plastic shrinkage and plastic settlement cracks, even though they are formed in the initial stage and even though they do not disturb the integrity of uh, concrete structure, the different fibers and different fibers, whether it is polypropylene or steel fibers or these materials, will add to the fatigue resistance, impact resistance, and some of the authors claim there is a small increase in terms of impermeability, things like that, tensile strength, and all this enhancement takes place. And overall durability also increased by using these kind of materials, especially in cases in tropical climate where the plastic shrinkage crack, plastic settlement cracks, if it is not treated, it may lead to ingress of materials. So in those cases, these materials like synthetic fibers, polystyrene, or sorry, polyester, or polypropylene, or any other kind of fibers which are added, can minimize the amount of formation of plastic shrinkage and plastic settlement cracks, and hence it will increase the durability because we need not have to treat these concretes again with a waterproofing treatment on top or something like that, and hence it will contain the amount of ingress of materials. So these metals also can be used for enhancing the durability of concrete. Next. So whenever we are selecting aggregates, coarse aggregates, and fine aggregates, they have to be as per codal provisions. If we have coarse aggregates with high amount of absorption, it will cause some problems in durability, especially related to drying shrinkage and creep. So we need to take care of the aggregate content. If the aggregate content is more, generally the dimensional stability and the durability of concrete is said to be better actually. So when we are talking about pumpable concrete and things like that, we have a tendency to go on increasing the sand content actually. So we have a choice. If we want to do this increase in sand content, we have to go on decreasing the water cement ratio to counter the effect of higher sand content. So aggregate content has to be managed judiciously, especially if we are talking about durable concrete. So we need to have a consideration of aggregate content and the quality of aggregates. Next one. So what type of concretes we are trying to use when we want to have a durable concrete? Okay. So when we have concrete with higher strength, it gives a choice for us, choice for the designer to use lesser concrete. Okay. It occupies lesser space. You are using lesser ingredients. Concrete with durability, when you are push the concrete to higher durability, okay, the service life of such structures will be more. You need not to go on repairing regularly. You have a choice to use lesser cement. If you use lesser cement, you know, every ton of cement, if you want to manufacture, we need to have about 1.5 to 1.6 tons of limestone. So quarrying of this, crushing of this, transporting of this, all this is a strenuous process. Also burning the these materials at about 1450 degrees, and production of carbon dioxide, all this is not sustainable. So if you use lesser cement, you are making the concrete more sustainable, and you are also preserving your limestone quarries and limestone deposits. Okay, so better to use lesser cement, and we know that when we are using optimized cement contents, we can push the concrete to greater durability, and also we can get sustainable concretes with this. We use lesser water. Okay, only 4% of the water available on this planet is said to be fresh water, and this fresh water we are using in different ways without considering the problems that we are causing to our next generation. So using less water is a very good idea in concrete, where you are pushing the concrete towards higher strength, higher performance, higher durability. Also, you are making a sustainable concrete. Next. So concrete, when you are using making a high slump concrete, you can say highly fluid concrete, highly pumpable concrete. Then your energies required for transportation and batching is reduced. So you don't have to use that much energy. It is more sustainable. And SCC is a big shift in concrete production and concrete technology as a whole. Actually. So SCC, where you avoid the vibration, where you avoid the human interference in the placing of concrete. You are pushing concrete to higher durability automatically. SCC concrete, most of the SCC concretes contain FCMs and low water cement ratio around 0.35 to zero point 0.5, zero point 0.4, and hence you are pushing the concrete to higher durability and higher sustainable concrete. Actually, there will not be honeycombs. The concretes of such concretes will be more moving towards high performance concrete. So concretes so designed will be durable, sustainable concretes with least honeycombing, high performance. That is how these concretes can be made to taken to higher level. Next. So we talked about the materials. We talked about the selection of materials. We talked something about mix design. We talked about what durability factors can be enhanced by using SCMs and SCMs in conjunction with high performance superplasticizer. We talked about those things. But that is only one portion actually. That is only one portion. We have production related factors which can go wrong, factors which has to be taken care during production and before production. So QAQC at batching plant or in a concrete producers facility is uh, is to be looked into actually. So whenever you are having a comprehensive QAQC system, it can be divided into three categories: forward control, immediate control, retrospective control. Forward control is a set of all activities that take place in a production facility before production. It is mostly related to QA. Immediate control is set of all activities that take place at the point of production. Retrospective control is those activities which take place after production, which cannot be done before production, which cannot be looked into or looked after before production. So forward control examples are how you are taking care of the batching plant, whether the calibration is done in the batching plant, whether the equipments are calibrated, whether you have selected right materials, whether your mix design is okay, whether the slump retention strength and all is okay, setting time is okay. All these things form set of forward control, including how you are storing the aggregates, whether there is intermixing, how your batching plant is, whether the batching plant is kept clean, things like that. Forward control means, as I said earlier, it is set of all activities that take place before production. Immediate control is set of all activities that take place at the point of production. How the batching plant operator takes care of the slump, whether he is feeding the moisture into the batch cabin, batch computer, whether the slump is measured, and how the slump is related to the slump at site. These things form the immediate control. Next set of activities, retrospective control. Once the concrete reaches the site, the cubes are taken on site actually, and after 28 days, after proper curing, the cubes are crushed, and there is a statistical control. Means data is analyzed, okay, and if there is any problem with respect to 28 distance, if distance are very close to characteristics, or if distance are very high. For example, M25 is giving M45. No point actually. This cannot be called as M25. So a concrete producer has to bring back to 29 or 30, something like that. So he has to do this retrospective control. So these activities form pillars of QAQC for a ready-mix company. So if you want a durable concrete, you need to have a look at a ready-mix company which is following all these systems. Also, you need to look whether they have qualified people on board actually. Okay, it is not only the systems, whether the qualified people are there on board to take your concrete order to higher degree of durability. Okay, it is not only the strength, we are talking about constantly of durability. So strength is one portion. Strength is you can say it is a for granted or automatically achieved. But we are talking about durability. If you want to have a durable concrete, the QAQC systems should have all these things in place. Next. So Once the once the concrete is mixed, once the concrete is mixed, you have a shelf life or a usable life, okay, of about 2 hours. IS 4926 clearly says once the concrete is mixed, you have to use within 2 hours, unless otherwise you have used a superplasticizer cum retarder, or you are using the concrete in winter conditions. That's what IS very clearly says. So you need to use the concrete once produced within 2 hours after the water has come in touch with the cement. So there may be some cases where you want to use the concrete for 4 hours or more than 4 hours. Then there should be proper trials conducted and proper data generated, and it has to be approved by the customer. Then you can use, you can change that one. Otherwise, the general trend is you need to use the concrete as early as possible. Since most of the concretes in India, most of the concretes are used with superplasticizer cum retarder. Superplasticizer cum retarder, we have type G STMC 494 type of admixture, where it allows the concrete to be transported and placed, and it has a setting time enhancement of plus 3 hours over control. So 3 hours extra it gives against the control concrete. So you can use the concrete for up to 3.5 hours maximum when you are using a superplasticizer cum retarder. But that is what most of the ready mix companies do it. But we need to be careful when we are talking about high durable concrete, high strength concrete, ultra high performance concrete. The cement contents or cementitious contents are significant. 450 and above will be there, especially when you are using a M60, making a M60 concrete. Let us say you have about 450 kg of OPC and maybe 25 kgs of microsilica or alkofine or metakaolin or things like this. This kind of, and you have a very low water cement ratio, maybe 0.3 or 0.28 or something like that. So the heat of hydration will be very fast. The C3A will be trying to react with water in a very faster way in the initial time. You cannot keep this reaction held or suppressed for longer time. So the C3A wants to react quickly with water, and hence you need to allow a smooth hydration to continue actually. So you cannot go on disturbing this one. So you cannot go on keeping the concrete intact and then go on tampering the concrete either with water or chemical admixture. So in short, what I want to tell you is higher grades of concretes, you should be very, very careful about the time of placing. You cannot prolong this concrete setting time for a long time, and hence it has to be used quickly. Otherwise, the disturbance you are causing to hydration will take a toll, and the durability will be affected actually. And such concretes may also exhibit plastic shrinkage and settlement cracks and things like that. So strength also may be affected. So you need to use the concrete in time to keep your concrete towards durability. You cannot. You have to have a proper supervision on site where the concrete is not over vibrated or under vibrated. We know if the concrete is under vibrated, every 1% of uncompacted concrete can lead to 5% drop in strength. So uncompacted concretes give lesser and lesser strength, and hence the people who are managing the vibration has to be trained well, has to be supervised well to achieve the design strength of concrete. And also we need to avoid honeycombing. If the improper compaction takes place, that will lead to honeycombing, and that is a big problem. It will cause a big problem pushing the concrete towards lesser durable material or problematic concrete. So we need to give proper importance to compaction and placing. And placing has to be done within a certain time, as defined by IS 4926, as defined by IS 4926. So higher grades, especially, you should be very careful. Next. Next. So the other point which we need to take care is proper curing. Initial curing, as soon as the concrete placed within about 1.5 to 2 hours, depending upon the temperature, wind velocity, and the humidity, you should start curing. We should start curing with a pesticide sprayer. Keep the concrete cooler. Then you can spread a plastic sheeting. You can use a plastic sheet. We should avoid direct contact with sunlight, or you should also avoid the wind effect. High speed winds take away the water, and when the rate of evaporation is lesser than rate of bleeding, plastic shrinkage cracks and plastic settlement cracks may occur actually. So we need to keep the rate of evaporation as less as possible, and that should be lesser than the rate of bleeding. You can use evaporation reducers. You can use a curing compound, but best way of curing is said to be water ponding. Curing with natural water is said to be the best method actually. Now, to ensure that the curing is not intermittent and curing is continuous, we need to employ or deploy a lot of labor, and supervision has to be of highest quality. Many times, if it is not done, the concrete will not reach its potential strength, especially the early strength. Early strength will be lost because we take the cubes from site to plant, and if it is not protected, and if it is not transported in time properly, and kept in water in time, you have strength loss issues actually. Okay. Okay, so initial curing is of very hello. So initial curing is very important actually. Abroad, many constructions they have started using internal curing compound. Internal curing compound. So this is a kind of a chemical admixture which can be added along with other concrete ingredients, just like a chemical admixture, so that you need not to bother about the curing. You need not to bother about curing. Especially useful for columns and areas where you need not have to. We can't have access to proper continuous curing. We can use this internal curing compounds. Next, next, next slide, madam. So now now once we have these once we have these fiber reinforced composite bars uh, are becoming popular in other countries, and where you have completely eliminated the problem of corrosion, because once the steel bars are eliminated, the corrosion to steel is eliminated, and you have pushed the RCC to next level of durability, very high level of durability. So these are being produced abroad, countries like Europe, China, and now now this is becoming more popular. This is becoming more popular and more acceptable. Next one. Next slide, madam. Now, Dr. Hank Junkers, Dr. Hank Junkers, from 2006 to 2015, made made lot of efforts to invent a material which is called as a self-healing concrete additive. Self-healing concrete additive. Basically, this product is based on bacteria. Some selected species of bacteria was taken, and it is encapsulated in some material, okay, in some polymers, okay, and this material can be added by about a certain percentage, like 1%, 1.5% to the total weight of concrete, say about at 5 kg or 10 kg per cubic meter. The beauty of this product is the bacteria which is encapsulated in these polymers. Okay, they are mixed during production of concrete, and once the concrete sets actually, and if there is any crack in the body of concrete, once the water and oxygen enters through the crack and touches these capsules having bacteria, they open up and they react with this oxygen and water to precipitate and generate some products closer to calcium hydroxide or calcium carbonate, and which will fill up the cracks. So whenever cracks open up, these bacteria gets activated and they react and fill up the cracks to make sure that the cracks are sealed very quickly. And such material have been tested in Netherlands in a big way, and they have found a great success. It is said that such material, such self-healing concrete, has a durability of 200 years. 200 years, as these kind of additives based on bacteria, based on the technology of capsuling the bacteria, certain species of bacteria, uh, can be always there in the body of concrete up to 200 years, and can go on sealing the micro cracks and cracks in the body of concrete structure, and hence can give significant durability enhancement as it will not permit the water and oxygen to enter into RCC structure. So that is how such concretes have been made, and now it is already being in the process of commercialization of this kind of product. So this is also a way to push the concrete to higher level of durability, higher level of durability. So next, next. So any of the I thank you. I thank all of you here who have come to hear this interactive session. Actually, most of you may be experienced in the world of concrete. You may have a great experience in receiving the concrete, producing the concrete, selling the materials related to concrete. If you have any questions, you can send through this chat actually, through a chat actually, or you can also ask the questions sending a mail to me. If you have any question, you can ask me now. You can ask me now. Hello, hello, hello. Any of you can send through a chat mode, or probably you can ask the question. Hello. Or you can always hello, hello.
Hello.
Yes, sir. Yes, sir. Good afternoon.
Sir, I have put two questions in the chat box already. Can you just have a look in the chat box?
Hello,
Hello.
hello.
Yeah.
Yes, sir.
Sir,
Tell me, sir.
I asked two questions in the chat box. Can you just have a look in that one?
Sir, somehow it is not properly audible. Can you send through a chat, or is it possible
No,
if hello?
sir, I put the questions in the chat box already.
Okay,
Please check the chat box. Sir.
Sir, your name, sir?
Uh,
Aishwarya, I'm not able to get this question also. I'm not hearing. I'm not able to hear what sir told actually, and also I'm not able to get the question actually. Can
Sir,
you
he said,
forward or
hello, sir?
yeah?
Hello? Sir, he is
Yeah.
telling that he has already sent the question in a chat box, sir.
Okay.
Sir, can you tell your name, sir? Hello? Hello?
Yeah.
Sir, we'll send them through mail, sir.
So some problem is happening, some network problem or something. Is it can you kindly send by mail actually? Can you send it by mail?
Sure, sir. I send it by mail. I send the questions by mail. Yeah.
Please.
Okay. Thank you.
Yeah, yeah, thank you.
Thank you, sir.